Hi everyone, I'm Julia, the chemistry tutor, and today I am going to talk about the basics of equilibrium. I am not going to go into the calculations involved with ice tables today for the concentrations and determining your concentrations at certain levels and at equilibrium and so on. I'm not going to talk about those in this video. I will do a separate video on ice tables for equilibrium. Okay, so today is the basics, the general ideas of equilibrium, and there are a lot of pieces and parts. So this video might be a little bit longer than I had anticipated or I would like. So let's get started. So far in your chemistry class, we have talked about reactions as if they go all the way to products, and that is that you get products from that. So for example, if we had, let's see, if I had sodium chloride reacting with magnesium sulfate, and we go this way, double replacement reaction, we make sodium sulfate and magnesium chloride. If you have a hard time with that, go back and watch my videos on types of reactions. Okay, and to balance that, I need 2 of those. All right, so we're balanced. Well, this theoretically could go the other way. I could be mixing magnesium chloride with sodium sulfate and making these. And so when I mix these 2 together, they form these products, but then these products start forming reactants. And it goes back and forth and back and forth. And when it reaches an equilibrium, when they are happening at the same rate, so when your forward and your backwards reaction, forward and reverse reactions are happening at the same rate, that's when we have reached equilibrium. Okay. And I'm not positive about that reaction right there. I'm not positive if that is a reversible reaction. I'm not really going to worry about that at this point because it's just the concept that we're talking about, that you can put 2 reactants together and they start forming products. But once they've made a certain amount of products, now those products want to go back and become reactants. So it goes back and forth, and when it's happening at the same rate, then we have reached equilibrium. So real quick, let me just talk about rate, right? So rate is a speed, like how fast is that happening? How fast are your products becoming reactants? How fast are your reactants becoming products? Okay, so that's the rate of the reaction, right? And we can increase the rate by increasing your concentration of reactants. And if we're talking about the backwards reaction, the reverse reaction, these are your reactants. So you can speed up the reverse reaction by adding more of those. You can speed up the forward reaction by adding more of those. Okay, so increase your concentration. You can increase your collisions. Right? Remember, chemicals react when they bump into each other. So say you could stir a solution, and that would increase the collisions and increase the rate of the reaction. You could increase the temperature, right? Because increase in the temperature increases those collisions as well, right? It makes them hit each other faster as well. You could increase the surface area. Okay, so for example, if you had a big chunk of something and you wanted to dissolve it, water can only reach the outside of that. But if you break it up into a bunch of tiny little pieces, now water can get to a lot more of it. So if you increase your surface area by like grinding something up or flattening it out, then you can actually increase your rate of the reaction. And we can add a catalyst. Okay, so if you add a catalyst basically grabs those molecules, those chemicals, and puts them together, makes them happen faster. Okay, so a catalyst does not affect the equilibrium. It affects the rate of the reaction, how fast it happens. Okay, so that's when we're talking about rate of a reaction, That's what we're talking about, the speed of the reaction. That is not the same thing as equilibrium. Okay, so reversible reactions, if we're thinking about reversible reactions, let's look at that as opposed to irreversible reactions, non-reversible reactions. So non-reversible reactions that will only have an arrow going one way. I don't know if I spelled that right. That might be an I in reversible. I don't know. So a non-reversible reaction would be like combustion, right? When you burn your propane in your grill at home, when you combust that into the carbon dioxide and the water, and you're heating that, those are gases, right? Those are off into the atmosphere. We can't grab that carbon dioxide and water together and put it back into our propane. We can't turn it back into propane and oxygen. Combustion is an irreversible reaction. The arrow goes one way. You cannot change that. Okay, so let me just real quick here balance those because that doesn't feel right to not have them balanced. There we go. Okay, so another example of a non-reversible reaction would be a neutralization. Okay, so like if I took sodium hydroxide and hydrochloric acid and mixed them together to make sodium chloride and water, right? This is just an aqueous solution of sodium chloride, right? Because sodium chloride is soluble in water. Well, you can't take salt water and turn it back into an acid and a base. Neutralization is a one-way reaction. You cannot reverse that reaction. And here, I wrote my notes up here. Let me just look here real quick. You also have rust formation. So like when you're forming rust, say you have an iron nail in the oxygen in the air, and it forms iron 2 oxide. It forms some rust. Okay, well, you can't undo that. You can scrape the rust off of the nail and expose new rust, but you can't turn the rust back into iron and oxygen gas. Irreversible reaction. Another example is when you, like your strong acids, when we did net ionic equations, strong acids, we split them 100%. Okay. So that doesn't go back. The hydrogen and the chloride never go back to become an hydrochloric acid all put together again. Okay, it likes to be separated. And in chapter 10, we're going to talk about how this actually has to happen in water. Hydrochloric acid won't split unless it's aqueous. You put it in water, and it actually splits into the hydronium ion and the chloride ion. Some of you have seen that. You're going to talk about that when you talk about acids and bases and buffers. Okay, but that's irreversible. A strong acid or a strong base in water, irreversible. You cannot turn that back into the together molecule. Okay, but when we're looking at reversible reactions, I really do think that's an I. Okay, when we're talking about reversible reactions, that's when we're talking about like weak acids. Okay, so remember in net ionic equations, we didn't split them apart. We said they don't separate, but they're weak electrolytes. So they do separate a little bit. There are some ions in there. Okay, so like if I had acetic acid, which is one of your weak acids, and I put it into water, some of that will split apart into hydrogen ions and acetate ions. Not very many, okay, but some of them do split apart. So we would actually probably draw the arrow where it's like a very small here and big here, saying most of it is here. Most of it is in that form. Okay, but that's a reversible reaction. And it's when you see a double arrow, doesn't matter what size they are, if one's small and one's big, if they're the same size, it doesn't matter. You see a double arrow, that means it is an equilibrium. That is a reversible reaction. Okay, so that's how we know we're at an equilibrium concept, is we have the double arrow. And sometimes that arrow can be written as just one line with an arrow at both ends of it. Okay, but either way, if you have an arrow pointing both directions, that is a reversible reaction, and we're talking about equilibrium. Okay, so there is, through experimentation and over the, many, many millennia that we've been doing chemistry, okay, maybe not millennia, but a lot of chemistry has been done. We've come up with a constant, we call it an equilibrium constant, KEQ. This is an equilibrium constant that tells us what concentrations these will be in relation to the concentrations of these at equilibrium. So depending on what molarity of this you put in, a certain molarity of this and this will form. Okay, and then they'll go back, and when we reach an equilibrium, they are at specific molarities. Okay, and that's what our equilibrium constant tells us. And the equilibrium constant is your concentration of products raised to their coefficients over the concentration of your reactants raised to their coefficients, and they're multiplied by each other. Okay, so for this reaction, my equilibrium constant, and we would say Ka because this is an acid. KEQ is just a generic equilibrium constant. Ka is specifically for an acid. So it'd be the concentration of my products, my hydronium ion, times my acetate ion over my acetic acid. Okay, something I didn't mention here is solids and liquids have no effect on equilibrium. So we do not put them in an equilibrium expression. So this is part of why when you did the net ionic equations, you had to be able to determine your states. Acids are aqueous, water is a liquid, any ion is aqueous. If it's got a charge, it is aqueous. So this water has no effect. So when I see the double arrow, I cross out solids and liquids because they're not going to have an effect. They're not going to play any part in that equilibrium. Okay, so our equilibrium constant is just the concentration of our products over our reactants raised to their coefficients. There were no coefficients in this equilibrium, so let me do another one that has coefficients to show you. So if I had hydrogen gas reacting with nitrogen gas is in equilibrium with ammonia gas. Okay, I don't know the size of those arrows. I don't know if it's more reactants or more products. Okay, but if I balance this, I get two of those and 3 of those. Okay, so my equilibrium expression here, so my KEQ, just a generic equilibrium expression, is my products, so the concentration of the ammonia, raised to his coefficient, divided by the concentration of my hydrogen raised to his coefficient, times my nitrogen, just raised to the 1 because he only has a 1. Okay, so that's your equilibrium expression. Okay, this is your equilibrium expression. We are expressing the calculation, how we would mathematically calculate our equilibrium constant, or if we were given the constant and 2 of these, we could calculate the other one. Right? Okay, so we can give you numbers for those, and you can use the equilibrium expression to calculate things. Okay, and I didn't really talk about very well up here. When we have those arrows, like if we have a long arrow going that way and only a short arrow going that way, and by the way, my arrow could be on the top going that way and on the bottom going that way. We really don't care whether it's top or bottom going which direction. They're just have your arrows there. Okay, so if I had this one Because the longer arrow is going more towards product, it means my equilibrium lies toward products. Okay, it means I will have more products at equilibrium than reactants. Okay, if I had my arrow were going more towards reactants and less towards products, and it could be the arrow on top could be the products, it doesn't matter. Either way, the longer arrow is going towards reactants, so your equilibrium lies toward reactants. So you will have more reactants at equilibrium than products. Okay, so if we think about K is your products over reactants, if you have more products, mathematically, you have a large K. Your K is larger. And basically, we could say larger than 1, right? Because more products, a larger number on top, your K is going to be larger than 1. If you're towards the reactants, right, a larger number on the bottom means that you have a smaller K, a K that is less than 1. Okay. So we do talk about the size of that K. And essentially, if your K is greater than 10 to the 3, you're definitely product or reactant favored. Sorry. Nope, product favored. Large K, product favored. Okay, over here, if your K is less than 10 to the negative 3, okay, but if you're in between the 10 to the negative 3 and 10 to the positive 3 in your K, you're pretty much equal. We kind of say that it lies right in the middle between products and reactants. Okay. So we have another value that's related to that K, and that is Q. That's your equilibrium quotient. Not sure I spelled that right. Your equilibrium quotient, and it's the same thing. Q is your products, concentration of your products, raised to their coefficients over your reactants, raised to their coefficients. And we compare it to K. If Q is equal to K, you are at equilibrium. You have your equilibrium concentrations. If Q is greater than K, right? If it's large, you have more products. So if Q is greater than K, you will shift. We're going to talk about shifts in a minute toward reactants. So basically, it's going to make more reactants in order to bring that Q down until it equals K. If Q is less than K, right, that would mean we have more reactants. So you're going to shift and make more products in order to bring it to equilibrium. So you're going to shift to make more products. Okay. So not every instructor in allied health chemistry talks about Q, but some of them do. General chemistry, they'll definitely talk about Q. Okay, so Q tells us if we are at equilibrium or not. And if we're not, which direction are we going to shift based upon is Q larger than K or is Q smaller than K? So let's do a little practice with the equilibrium constant that we've been talking about. So your equilibrium expression. So we're going to answer each of the following in the space provided. So what is my equilibrium expression? That is my K for this reaction. They're all gases, no solids or liquids, so we don't need to worry about that. So we're going to remember K is your concentration of products raised to their coefficient over the concentration of the reactants raised to their coefficients. So I have my K is equal to hydrogen iodide raised to the 2 divided by hydrogen and iodine. Let me make that a little bigger. Okay. So my products raised to their coefficient. My coefficient was 2, so I raised it to the 2. These only had 1s in front of them, so I didn't raise them to anything because it's already 1. Okay, if we look at this next one, okay, my K, and you can put EQ, or some instructors let you just write K if you don't know what it is. It's just a generic equilibrium. Okay, so for this one, I have my products. So my concentration of ammonia, and it's only a 1. My hydrochloric acid is only a 1 divided by, oh, look, that's a solid. So we're not going to put it in there. We're not going to pay attention to it all. It's just basically over 1. Okay, if we're going to leave it out, the solid or liquid, you can just put a 1 there, which that is just ammonia times HCl. Okay, because the 1 is just a 1. Okay, so for this one, we look and we immediately, solid, solid, so we cross those out. So my K is going to be equal to my carbon dioxide raised to the 6 times my arsenic, and that's it. This over 1 because those are both solids. Right, so on this next one, I've got a solid. I'm going to cross it out. So my K for this one is my products. So my carbon dioxide raised to the 2 over my tin-4 oxide. Oh, there's another solid. I almost put that one in there. Cross that out. So over my carbon monoxide raised to the 2. So we just leave those solids out. So for this next one, I've got a solid here. I've got a solid here. So my KEQ for this one is just equal to the concentration of my carbon dioxide. Okay, I know it feels weird, but that's it. You just leave your solids and liquids out. There were no liquids here, but you just leave your solids and liquids out and put your products raised to their coefficient over your reactants raised to their coefficient. So let's do a few actual problems with those. Okay, so for number 11 here, so we've got this reaction going on. We've been given our K. So at some time, the following concentrations are, we have our carbon monoxide and our carbon dioxide. And it wants to know if it's at equilibrium. Okay, which means we're going to calculate our Q to find out if we're at equilibrium. So first of all, we cross out that carbon because it's a solid. So we know our equilibrium expression is the concentration of our carbon dioxide raised to the 1 times our carbon monoxide raised to the 2. So we've been given that our carbon dioxide is 3.6 times 10 to the negative 17. And that's going to be divided by the carbon monoxide, 0.034 squared. Okay. Okay, so when I do that, I get 3.1 times 10 to the negative 14. And by the way, K has no units. There are no units on K. All of your molarities cancel out. We're not going to worry about how that happens, but there are no units on K. It's just a number. Okay, so now that is our Q. Actually, we just calculated the Q for that because those are at a particular time. we are not necessarily at equilibrium. That's what we're trying to figure out. Are we at equilibrium? Okay, so we're going to compare it to our K. Our K is 7.7 times 10 to the negative 15. Okay, so this number is larger than K, right? And negative 14 is closer to 1 than negative 15 is. So this one is your larger, so your Q is larger. So if your Q is larger, you have more products, and so you are going to shift to the left towards reactants because you have more products. Okay. We'll go back and do a couple more of those Q calculations. I want to do some just general equilibrium constant things, okay? So here we are. This one is at equilibrium. So this one we know we're talking about K. On the last one, it was at some point in the reaction, which you have to discover whether or not you're at equilibrium, okay? This one tells us we are at equilibrium. Okay, and so let's see, does it tell us? Oh, it does give us an equation. So we've got a gas, and a gas, so we don't need to cross any of them out. So write the expression. Your expression is your K, so your KEQ is equal to your products, so your AB raised to the 2 over your A2 times B2. And these are just generic chemicals. Okay, we don't care what they are. They can be anything. It's still products over reactants. It doesn't matter what those chemicals are. Okay, so now if we're going to find the value for K, find your value for KEQ. We know that our KEQ is that. That's our equilibrium expression. So now we're going to plug in our concentrations for those into that expression. So our KEQ is equal to concentration of AB, which is 0.67, and that's going to be squared, divided by the A2, which is 3.45, times on the bottom 5.67 for the B2. And then you just calculate those numbers. And when I calculate that, I get 0.2294 and some numbers. And we are at 2 sig figs here, 3 and 3. So we're going to go with 2 in our answer. So I get 0.23. And remember, K has no units, so it's just 0.23. Okay, so you see if they give you the concentrations, you just plug them into the equilibrium expression. So let's do another one. Okay, so we've got another generic. They're all gases, so we don't need to cross anything out. Our equilibrium expression is our products. So our XY, XY3. And that's going to be squared divided by the x2 to the 1 times y2 cubed. Equilibrium expression. Products raised to their coefficients divided by reactants raised to their coefficients. And they said here that K is temperature dependent. By the way, I didn't mention that. So if they tell you the temperature, you're going to be running it at the same temperature. It's just more information because K is temperature dependent. At a different temperature, it will be a different K value because like if you're dissolving a solid at a higher temperature, more of it is going to dissolve. So you're going to have more products at equilibrium for that than you would at a cooler temperature. So K is temperature dependent. So when they give you a temperature, they're just saying that's the temperature, the K is at that temperature, and hey, we're going to run it at that temperature. They seldom change the temperature on you. I actually cannot think of a time when they change the temperature on you. Okay, so now we're going to calculate K by just plugging those into that equilibrium expression. So my XY3 on top, so that's going to be the 0.090, and that's going to be squared, divided by my X2, which is 0.37, times my Y2, which is 0.53, and that one is cubed. And now we just calculate that. And when I calculate that, I get 0.1470, and I'm at 2 sig figs here, 2 here, 2 here, so 2 in my answer. 7 will round the 4 up, so I get 0.15. And taking into our idea that, right, if K is larger than 1, you have more products. Your equilibrium lies towards products. If it's less than 1, your equilibrium lies towards reactants. You have more reactants. So both of these are less than 1. Both of them, the equilibrium lies towards more reactants. You will have more reactants at equilibrium than products. Okay? So that is how we use the values given to us to calculate our K. Okay, so here is another one. It's another generic reaction. They're all gases, so we don't need to cross any of them out. So the concentrations were found at, it's an equilibrium. Okay, so we need to calculate the equilibrium constant, calculate our K. So our KEQ is going to be the concentration of C over the concentration of A times B. So my C, 0.30, divided by my 0.45 times my 0.63. Okay, and then we just calculate. And I get 1.0582, and I have 2 sig figs, 2, 2, so 2 in my answer. The 5 will round the 1 up, the 0 up, so I get 1.1. So this one lies more towards products because your K is larger than 1. Okay, and so now we have at the same temperature, so we're looking at the same K, at another equilibrium mixture is analyzed, and it's found that we've got these concentrations. Okay, so now we need to calculate A. So we know that our KEQ using this equation, that's our equilibrium expression. Our KEQ is 1.1. We know that C is 0.70. We know that A is what we're looking for, and B is 0.21. Okay, so remember, if we're solving for what's on the bottom, your easiest way to do this is to flip the entire equation. Get your x on top. So I'm going to flip that, so I get 1 over 1.1 is equal to 0. I forgot to flip that. Is equal to x times 0.21 divided by 0.70. Okay, and remember when we're isolating that, we're just going to move these to their diagonal across the equal sign. So I get 0.70 times 1 divided by that 1.1 times the 0.21 is going to be equal to my concentration of A. And then we just calculate it. And when I calculated that, I got 3.0303. And we've got 2 sig figs here, 2 here, 2 here. So I'm going to go with 2 in my answer. So the concentration of A is 3.0 molar. Remember, concentrations are in molarity. K's have no units on them. Okay, so let's do one more of those Q questions. Okay, so if I'm looking at, let's do, we'll do, wait, I'm trying to find one that I want to do. Oh, let's do number 14. Okay, so if we look at number 14, iron oxide is a solid, I'm going to cross it out. Iron is a solid, I'm going to cross it out. So we're looking for find Q and which way will the reaction proceed if it's not at equilibrium. So we have our K is going to be equal to our products over the reactants. Okay, so now we're just going to plug those numbers in. So I have that my water is 0.37, and that's going to be cubed. And my hydrogen is 0.45, and that is also going to be cubed. So now we calculate that. And I get 0.55586. And I'm at 2 sig figs here, 2 here, so 2 in my answer. 5 is going to round 5 up, so I get 0.56. And it told us our K is this, 0.064. So Q is a lot larger than K. So I have a lot more products, right? My products are larger on the top, so my Q is larger than K. So I am going to shift to the left to make more reactants. Okay, so let's go ahead and answer these questions down here real quick. Okay, so if my equilibrium concentration of products is greater than that of the reactants, okay, so this is not looking at Q, this is just looking at K, right? So K, we said if K is larger than 1, we have more products. If K is less than 1, we have more reactants. And if K is equal to 1, products equals reactants. Okay, and remember, we're just looking at that as products over reactants. If this is larger, my answer is larger. If my reactants are larger, my answer is smaller. Okay? So if our equilibrium concentration product is much greater than that of the reactants, then my Q is much greater than 1. If the equilibrium concentration of products is less than that reactants, much less, that means we have more reactants, so K is less than 1. And if there's a considerable amount of both, if they're about equal, then your K is about equal to 1. Okay, so that's pretty much what I'm going to talk about with K and Q and all of that. Now we're going to start talking about the shift that I'm discussing there. Okay, so now to discuss the shift that I was saying, we're going to shift to the left to make more reactants because we have too many products. Okay, so that is Le Chatelier's principle. Okay, and Le Chatelier says that when something is out of equilibrium, things will shift in order to come back to equilibrium. Okay, and so equilibrium, the shifting, the whole concept of it is a teeter-totter. And I'm sure at some point in your life you've played on a teeter-totter or a seesaw. Depending on where you grew up, they call it different things. Okay, so if you're on a teeter-totter, okay, this is your fulcrum point. Okay, in a reaction, here's your reactants, and here's your products. Okay, so the fulcrum point on the teeter-totter is your arrow on your reaction. Okay, so I'm sure at some point in your life you have thought about or even tried to get some friends on the teeter-totter, some on this side and some on this side. and to make it level, to make it even. That is equilibrium. You're level on both sides. Okay, so what if I add a kid to this side? Now I'm heavy over here, correct? So I'm going to have to shift that kid that direction in order to make it level again. So you shift away from additions. Anything you add, you shift away from it. Because now we have too much product, we need to shift over to make more reactant and less product to make that K be the same, because it is a constant. Okay, so what if I had same teeter-totter, same idea going on, but let's say and we're pretending those kids are the same weight. Okay, if some of them were smaller, right, we would have maybe more on one side to make that weight be level, weight be the same. Okay, but what if I take a kid off of that side? Now I'm heavy over here, and I have to shift that direction in order to make it level again, right? I'm going to have to move that kid kind of to the middle, shift that way. So we shift toward anything that we remove. Toward removals, away from additions. Okay? And I could have done that same stuff. I could have done it all on the reactant side. It doesn't matter which side you're talking about, the reactants or the products. Okay? You're just throwing it all into the container. And if it's products, it's going to shift one way. If it's reactants, it's going to shift one way. Okay? It's all in the same container, all in the same beaker. They're all on the same teeter-totter. It's just which way is it going to shift depending on what you add or remove. Okay, so a couple things to think about with this is, wait, hold on. Let me think for a second. Okay, so for example, if I had a reaction that my K was 50. Okay, so my K is 50. And let's say that my products was 200 and my reactants was 4. So that's at equilibrium. Okay, so it lies much more towards products because that's 50. It's a lot greater than 1. You have a lot more products. Okay, so let's say that I add more products. Okay, let's say that I add products until that's at 8 and the reactants are still the same at the moment I'm adding products. So now this equals 25. Well, this is a constant. It has to be 50. So what's going to happen is there's going to be a shift that occurs. Okay, we're going to have a shift. I don't want to make that an arrow because we don't know which way. Well, we would be shifting towards reactants, but we're not going to worry about that. So when we shift, we're shifting towards products. Sorry, oh my goodness, I messed that up. I just added reactants. Reactants are on the bottom. Sorry about that. So I doubled my reactants. I made more reactants, which messed my K up. Well, now I need to shift in order to make the K equal 50 again. So I shift, and I am shifting towards products in this case. Okay, so I shift to where that's going to equal 50 again. So I'm going to make more products, use up some of those reactants. So now my equilibrium concentrations are different because I added some of those reactants. I shifted to make more products. I used up some reactants to make products. And the whole reason for this is to make our constant be the same. Okay, so that's what I'm talking about shifting. Why we're shifting is we're shifting in order to make the equilibrium constant stay the same number. Okay, so let's do a little practice with those. Okay, so we are looking at this reaction. Okay, and I have not yet talked about this kcal up here. Okay, so basically that is just heat. Okay, and heat is a product. We're going to talk about this in a minute. This means it is an exothermic reaction. Thermic being heat, exo meaning it exits. It is a product. Okay, but just keep it in mind that's on the product side for right now. We're going to talk about endo and exo in a minute here. Okay, so it already gave you the first one. Okay, so if we add some nitrogen, I'm adding reactants. I'm going to have to shift to the right in order for my equilibrium constant to go back to the regular number. Okay, well, nitrogen is what was added, so it's not going to affect that. Okay, but if I shift to the right, I'm going to use up some hydrogen. So the concentration of hydrogen decreases. I'm going to make more ammonia, so the concentration of ammonia increases. And remember, K stays the same, except for temperature. If temperature is involved, K changes. K is temperature dependent. Okay, so now let's do one on our own. Okay, so now I'm looking at adding H2. I'm adding some of that, so I'm going to shift away from it. So I'm going to shift to the right. And when I shift to the right, I'm going to use up some of that nitrogen. So it's going to decrease. I'm going to use up, oh, we're not looking at what hydrogen does because that's what we added. Okay, but I'm going to make more ammonia, so that's going to increase, and my K remains the same. Okay, when I look at my next one, I'm going to make my marker a little bit bigger for this. Okay, so if I add ammonia, okay, so I'm adding more of this. So I'm, oh, sorry about that. So I'm adding more ammonia. So I'm going to shift away from it towards reactants. And what is that going to do to my nitrogen? I'm going to make more of it. What's that going to do to my hydrogen? I'm going to make more of it. The ammonia was what we added. And my K stays the same because we didn't do anything to the temperature. Okay, so if we look at the next one, if I remove into, so I'm taking that away. So I'm going to have to shift towards it to replace it. I'm going to need to make more of it because I removed it. So we're going to shift towards reactants. The effect on nitrogen is that's what we removed. The effect on hydrogen, if I'm shifting towards reactants, I'm going to make more hydrogen. And I'm going to use up some of my ammonia to do that. And the K stays the same because temperature was not involved. Okay, what if I remove hydrogen? So now we are removing hydrogen. So now we need to shift towards it to make some more of it. So we're going to shift towards the reactants. The effect on nitrogen is we're going to make more of it. The effect on ammonia, if we're shifting away from it, we're using it up, we're going to decrease it. And K stays the same because temperature was not involved. Okay, so now what if I remove ammonia? So if I remove ammonia, I need to shift towards it to make some more. So I'm going to shift towards products. What's that going to do to my N2? I'm going to use some of it up. So I'll decrease the concentration. My H2, I'll use some of it up, decrease the concentration. And my K stays the same because temperature was not involved. Okay, so now we're getting to temperature. Okay, so remember, this right here is temperature, that's your heat. So if I increase heat, if I add heat, I'm going to shift away from it. So we're going to shift away towards the reactants. What's that going to do to my nitrogen? I'll make more of it. What's that going to do to my hydrogen? I will make more of it. What's that going to do to my ammonia? I'm going to use some of it. So I'm going to decrease the concentration, and temperature was involved. your temperature changes. Your K changes. I'm not going to talk about how much it changes or if it goes up or down. I would honestly have to do some serious thinking about that. So I'm not going to talk about that right now. Okay, so now what if I decrease the temperature? So if I decrease the temperature, I am removing heat. So I'm going to have to shift towards it because I removed it. So we'll shift towards products. What's that going to do to my nitrogen? I'm going to use some of it up. My hydrogen, I'm going to use some of it up. My ammonia, I'm going to make more of it. And because temperature was involved, your K changes. Okay. So now pressure and pressure. Okay, pressure and volume essentially. Okay, so I did not talk about that earlier. Let me pop over here. So pressure and volume affect only gases. Remember, that's really the only time we've talked about pressure is when we're talking about gases. Okay, so if you increase your pressure, do you agree with me? That's pushing your gas closer together, those gas molecules closer together, which is essentially decreasing your volume. And think about it like in terms of a balloon. If you have less volume, more pressure, then you have less moles of gas. You can have less gas in there. So if you increase your pressure, which also decreases your volume, you shift to the side with less moles of gas. Okay. If we were to decrease our pressure, which increases our volume, we have more space for gas, more moles of gas. The pressure is less, right? We've got more space so the gas can spread out, not much pressure on it. Okay, so we're going to shift to the side with more moles of gas. Okay. If there's no gas in it, then it has no effect. Okay, or if there's only gas on one side, so like if I had, let me think of one that has a gas on one side. Oh, so if I were decomposing baking soda, and that's going to make sodium carbonate, water vapor, and carbon dioxide, and this is a solid. Okay, I have two gases over here. Well, this is not really an equilibrium. Okay, so pretend that's an equilibrium. It's not. You cannot undo a decomposition reaction. You can't turn those back into sodium carbonate, bicarbonate. Okay, but just pretending if we were at equilibrium, we have 0 moles of gas here and 2 moles of gas here. Okay, so keep in mind, if there's no gas, that is just 0 moles of gas. You can still compare the two sides. If there's no gas at all, pressure and volume have no effect on equilibrium. So let's go back here. Okay, so we are increasing our pressure, which decreases our volume, so less space for gas. So over here I have 1 and 3, so I have 4 moles of gas here. And over here I have 2 moles of gas. Okay, so if I increase my pressure, I decrease my volume, I'm going to shift to the side with less moles of gas over towards the products. What does that do to my nitrogen? Oh, I can't make that smaller. What does that do to my nitrogen? If I'm shifting away from that, I'm going to decrease my concentration of nitrogen, decrease my concentration of hydrogen, increase my concentration of ammonia, and because temperature was not involved, there's no change in your K. So now if I decrease the pressure, increase in the volume, right, I'm going to shift to the side that has more moles of gas. So I'm shifting that direction. What's that going to do to my nitrogen? I'm going to make more of it. I'm going to make more of my hydrogen, and I'm going to use up some of my ammonia. Because temperature was not involved, your K stays the same. All right, let's do one more of those, and then we'll do some endothermic and exothermic graphs to talk about that, and then we're going to call it a day. Okay, so I'm looking up here at this reaction. Okay. And remember, solids and liquids have no effect on equilibrium. So we are just going to cross out that solid. We don't care about it. Okay. So when I look at adding that solid, no effect. And it's no effect all the way across. Nothing happens. Okay. So now if I add some sodium chloride, if they didn't give you this hint, sodium chloride is not in this equilibrium, but sodium chloride is soluble and you get a sodium ion and a chloride ion. So you are adding sodium. So if we add sodium, we're going to shift away from it. So we will shift towards the reactants. What is that going to do to my amount of sodium of this? It's going to increase it. Okay, so remember, the solid gets affected, but it itself does not affect the equilibrium. Okay, and I'm going to use up some of my hydroxide to do that, so decrease that concentration. K stays the same because temperature was not involved. So if I add KOH, group 1 metal, always soluble, so I get potassium ions and hydroxide ions, so I'm adding hydroxide. So if I add hydroxide, I'm going to shift away from it to the reactants. That's going to increase my sodium hydroxide, decrease my sodium ion because I'm using some of it up, and my K stays the same because temperature was not involved. Okay, so what if I add hydrogen ion? So this is something you need to think about. Hydrogen ion reacts with hydroxide ion to make liquid water, essentially removing it from the system. So if we add hydrogen to a hydroxide, we make water and we remove that hydroxide from the system. We're taking it away. So we're going to have to shift towards it to replace it, which means we are going to use up some of our sodium hydroxide. We're going to increase our sodium, right? Because we're going to add more to that side and our K stays the same because no temperature was involved. Okay, and so now when we're looking at temperature, okay, this says my calories are over here on the product side, so heat is over here. Okay, so if I increase my temperature, I'm adding heat, so I'm going to shift away from it. So I'll shift towards reactants, which is going to increase my sodium hydroxide, decrease my sodium ion, and decrease my hydroxide ion. And your K will change because temperature is involved. We actually probably can see how K is going to change in that. I don't know. I'm still not going to talk about it because I'm not completely clear on it. I might come back to it in a minute. Okay, so now if I decrease my temperature, I am removing heat, so I need to shift towards it to replace it. So I'm going to use up some of my reactant and increase those products. And because it was temperature, your K is going to change. Okay, so now on pressure, we look up here and we don't have any gases in that equation. No gases, no effect. All the way across. Decreased pressure, again, no gases, no effect. All the way across. So I hope that makes sense. I'm actually going to stop for a second and check on that temperature thing. I'll be back. Okay, so there is a way to tell if your K is going to go up or your K is going to go down based upon the temperature changes. And for that, you would use what we call the Van 't Hoff equation. In Gen Chem, you would do that. Okay, in Allied Health, you would not do that. You're not going to go that far into it. I'm not going to go into that in this video because, as you saw, I had to even go look it up. So I'm going to have to familiarize myself with that equation before I could really talk about it. Okay, so at this level, we're just saying if the temperature changes, we know the K is going to change. Okay, so now I'm going to talk about endothermic and exothermic. So endothermic, thermic meaning heat, endo meaning enter. So I remember en, enter. So heat enters. So heat is a reactant because it enters the equation on the reactant side. Sorry. Okay, exothermic. Thermic meaning heat. Exo, exit. So heat exits in an exothermic reaction and it is a product. So in this case, let me write that underneath so it doesn't get confused in the same thing. So in this case, heat is a product. Okay. So you're going to remember it very easily by endothermic and exothermic. And the units we use on heat can be either kcal, kilojoules, or joules. Okay. So typically, sometimes they might say just heat over here, or they might give you a specific number of kcals, calories, kilojoules, joules. Same here, they might give you a specific number. Okay, one other thing to think about with this is delta H means change in heat. It's actually change in enthalpy. If you're in general chemistry, that's change in enthalpy. We can just call it change in heat. So how much does your heat change? Okay, so if heat enters on this one, I have a positive delta H because heat increased. I added heat. And down here, I have a negative delta H because heat decreased. I removed heat. Okay. So they might talk about that in terms of they'll put it on the side of the equation, or they might tell you what your delta H's are, and you have to put it in on the side of your equation. Okay, so one of the things that we do with that is we talk about potential energy diagrams. Okay, and we have two of them, one for endothermic and one for exothermic. Okay, I'll put endo here and exo here. Your y-axis is energy or heat. Heat is energy, by the way. So the y-axis, and this is as your reaction progresses on the x-axis, which could also be seen as time, right? As time passes, as the reaction progresses. Okay. So in an endothermic reaction, we're adding heat to it. We're adding energy. So we start at low energy and we end at a higher energy. We'll talk about that hump in a minute. For an exothermic, heat exits, so we start higher and we end lower. Okay. So those are the points on the graph that are important: the beginning, the end, and the top of that hump. Okay, those are important spots on the graph. Okay, so every reaction that happens has to overcome an energy barrier. Like you have to put them together, you have to mix them, you have to do something. So it first has to overcome an energy barrier, and that's called the activation energy. So your activation energy is from the start to the top of the hump, because that's how much energy it has to go through in order to get going. It's kind of like if you're going skiing, you got to climb that hill first. That is your E sub A. That's called your activation energy, E sub A. Okay. Your change in energy is from the start to the end. Okay, so from my start to my end, that's my change in energy. In this case, that was energy absorbed because we added energy. Okay, and is there one more thing? Okay, let's talk about over here are your reactants. You have only reactants. Over here you have products. And here is what we call the activated complex. It's kind of like the middle step, right? As reactants are becoming products, it's that middle step. Okay. So, and to put this out there, if we were talking about the reverse reaction, okay, the reverse reaction, let's see, so for your reverse reaction, your A sub E is this, or your E sub A for your reverse reaction. Okay, your change in energy for the reverse reaction is, the same. Right? But your activation energy changes, right? For the activation energy, if we flip that graph, that becomes an exothermic graph, and you don't have to overcome as much energy. Okay, so for an exothermic reaction, okay, let me go back to blue. Okay, so for an exothermic reaction, my change in energy isn't as much, right? My activation energy. My activation energy isn't as high because I still need to put some energy into it to get it started, but because it's going to release energy, I don't need to add as much as the beginning. Your activation energy is much smaller. My change in energy from the beginning to the end, okay, and it just depends on that reaction, how much your change in energy is. You can absolutely say that for an exothermic, you have a smaller activation energy, and for an endothermic, you have a larger activation energy. But for the change in energy, you can't really say specifically. Okay. Okay, and if we were to reverse that, like I reversed the other one, right? The reverse of it, your change in energy would still be the same. But your activation energy would be much higher because now you are reversing the reaction, turning it into an endothermic reaction. Okay. So if you're running a reverse reaction, your energy diagram just reverts from endothermic to exothermic or exothermic to endothermic. They just switch on each other. Okay, so we're going to do a couple of practice with those. Okay, so I drew a little energy diagram here, and so we're going to answer a few questions with this. But the first thing you want to do is you want a line at your beginning, you want a line at your end, and you want a line at your top. Okay. Okay, so when we look at this, it's asking, is this an endothermic or exothermic reaction? Our energy at the beginning is lower then at the end, so we added energy, so endothermic, heat entered. Delta H for an endothermic, I'm adding heat, so I'm going to have a positive delta H. Now, if I look at the value for delta H, right, my change in energy is from the beginning to the end. Okay, so I ended at 100 kilojoules minus my 50 that I started with. 50 kilojoules is my change in energy. Okay, it's my delta H. Okay, my E sub A for the reaction is the beginning to the top of the hump. Okay, so my top of the hump minus the beginning is 200 kilojoules. Okay, the energy of the activated complex, remember your activated complex is up at the top. It's where you're finally like activated, ready to slide on down that hill. So your energy of the activated complex is the 250 kilojoules. Okay, now the E sub A for the reverse reaction. So your activation energy for the reverse reaction, going to change my color, is from the end to the top of that hump. Okay, so for the reverse reaction, I ended at 250. Oh yeah, 250. Oh, I'm not going to go back to purple. Minus the 100, right? That's 100 there. So it is 150 kilojoules. Okay. And if I looked at my change in energy for the reverse, okay, my change in energy for the reverse is, I'm going to go back to purple, is my beginning to the end. But this time we ended at 50 kilojoules and we started at 100 kilojoules. So that is negative 50 kilojoules, right? Because the reverse reaction would have a negative change in energy, right? Okay, so my delta H for the reverse reaction is the negative 50 kilojoules. Sorry, delta H, which is the same as delta E. Okay, so that's how you look at a potential energy diagram. It's how you draw them, right? A endothermic starts lower, ends higher. Exothermic starts higher, ends lower, right? Activation energy from the start to the top of the hump. Change in energy from the start to the end, right? What you started with, what you ended with, that's your change in energy. Activation to get you to the top of the hill so you can ski down. So I do believe that is all. Oh, nope. Let me add a catalyst to those. Okay, so remember we said that a catalyst doesn't affect the actual place of equilibrium. It just makes it happen faster. So if you put a catalyst into this, all a catalyst does is it lowers the activation energy. Okay, so a catalyst lowers the activation energy. Okay, it starts at the same place, ends at the same place, right? So your change in energy is exactly the same. It's just that your activation energy is lower. So you don't have to get as high of energy to get started. So the reaction happens faster. Remember, it just increases the rate of the reaction. Okay, so it can form that activated complex faster, right? Which, remember I was saying a catalyst like grabs those molecules and puts them together. So they're collisions, right? There's more collisions. They're more likely to reach each other, more likely to be activated, more likely to react. So the catalyst just decreases the activation energy, makes the reaction happen faster. So I believe that is all I have to say about equilibrium. That was a lot of information. And like I say, I will do a different video on doing the ice tables to get specific concentrations and so on. Okay, so yeah, that's all I have to say about equilibrium today. So have a great day.